In our previous lectures, we have used many times the words stable and unstable, especially when we were talking about the pendulum. And in this lecture, we will finally give the precise definition of stability, asymptotic stability, and unstability or instability of an equilibrium point of an autonomous nonlinear system. Okay, so therefore the object of interest is the autonomous system x that equals f of x. Okay, and under the title stability, we will investigate the behavior of the solutions of that system around some equilibrium point. Okay, so this is the autonomous system. Let's call it system 1 with the state residing in Rn. Therefore, the right hand side f is a mapping from Rn to Rn. Okay. Now, we have seen in the previous lecture that the solutions for a general nonlinear system, they don't have to exist. If they exist, they don't have to be unique, and they don't have to exist for all future times. But for simplicity, through other arguments to follow, we will assume that the solution always exists. It exists uniquely and for all future times. Okay, starting from initial time t0, and without loss of generality, we will take t0 to be 0 because the system is time invariant, and it's defined for all future times up to t equals infinity. Okay, so let's put that implicit assumption here, unless otherwise stated. The solution x of t of our autonomous system 1 uniquely exists for all initial conditions. x0 equals something in Rn, okay? 0 being our initial time. And for all times. Times t in 0 infinity. Okay, so that's our implicit assumption. Now, the goal that we pursue here is the following: study and characterize the stability of an equilibrium of the system x equals f of x. That's called x bar. X bar is some point in Rn of the system. 1. That is, remember the definition of any point. It's a solution of the equation f of x equals the 0 vector. Now, by a coordinate change, even if x bar is different than the origin, you can always redefine your coordinate system so that x bar becomes the origin of your new coordinate system. Okay? Hence, without loss of generality, and because it provides some notational advantages, we let x bar to be the origin. So we're going to be interested in the stability properties of the origin. Okay? Okay, and origin, it does not have to be the only equilibrium point of the system. Okay, without loss of generality. We will let x bar to be the origin. Okay, now we're ready to give our definitions of stability, instability, and asymptotic stability of an equilibrium point. Note that there's also there are many different types of stability in the nonlinear domain, and the other important kind is the stability that studies the relation between input and output, and that's for later. Okay. For now, we're interested in only this autonomous system, which doesn't have an input, and we're interested in the behavior of the solutions about an equilibrium point. Okay. Now, this definition is what we will be using in our future investigations. Okay. Now, a system, an equilibrium point of a system is stable if, qualitatively speaking, if you pick your initial condition close enough to the equilibrium point or to the origin, it will always remain in some sense close to the origin, okay, for all future times. So that's the definition of stability. And if it's not stable, then that means then we're going to define such, we're going to define such equilibrium point as unstable, and if on top of stability the solutions also display the behavior that as time goes on they converge to the equilibrium point, then we're going to call that stronger definition, stronger behavior, asymptotic stability. Okay. Now, here goes the exact definition. The equilibrium x equals 0 of the system 1 x equals of x is said to be stable. Okay. If you start close enough to the equilibrium point, you stay close to the equilibrium point for all future times. Okay. More rigorously, if for each positive number, call it epsilon, there exists delta, another positive number, such that x0, the distance of the initial condition, initial state to the equilibrium point, to the origin, is, if it's less than delta, then the position of, or the distance of the solution at any time in the future is never larger than epsilon. For all t positive. Okay, so that's the definition of stability. Second, unstable. Okay, the equilibrium point is said to be unstable if this condition fails, if it's not stable. Okay. A common grammatical mistake that's made by people is that they use the word stable to talk about the system, or to define the system, to characterize the system. They say such and such system is stable. Okay, so in a sense, it's okay if implicitly the person that you're talking to is aware of the particular equilibrium point that you're referring to. Okay, but in general, it doesn't mean it's senses to say that the system is stable in the following sense. For instance, consider the pendulum. Okay, so that system, okay, swinging pendulum, is it stable or unstable? It doesn't make sense to say that it's stable or unstable because it has two equilibria, and one of them is stable and the other is unstable. Therefore, it's not correct to say that pendulum system is stable or pendulum system is unstable. The correct way to put that information is that the downright equilibrium position, okay, is stable for the pendulum system, and the upright equilibrium position is unstable for the pendulum system. Okay, so once again, stability is not a property of the system, but the property of the equilibrium point of the system, which there may be more than one. Of course, for linear systems, the equilibrium point is always the origin, or the equilibrium point of interest is always the origin. Therefore, it has become the integral part of the definition that we talk about stable linear systems. Okay, but by that we mean linear systems whose origins are stable or unstable. Okay, so that's our simple definition of stability, and then you can strengthen this condition by adding an extra condition that if you start close enough to the origin, all the solutions, okay, they remain bounded. That's one thing. You know, in addition, they also converge to the origin. Okay, if that's satisfied, that condition is satisfied, and then such equilibrium point is called asymptotically stable. So that's our third sub-definition. Asymptotically stable. Okay. If it's stable, so that's the first condition to satisfy. Okay, this condition holds plus and delta can be chosen so that x0 less than or equal to delta. Okay, if you start close enough to the origin, then the solutions, they remain bounded. Okay, because we are assuming that the equilibrium point is stable. In addition to that, they also converge to the origin. Okay, as t goes to infinity. Okay, and this behavior that the solutions converge to the equilibrium point is called attractivity property of an equilibrium point. Okay. It's called attractivity. So with that, well, new term introduced, we can say that an equilibrium point is asymptotically stable if it's stable and attractive. Okay. Now let's visualize these simple definitions for a second order system. Let's say, suppose that we have a stable equilibrium point, the origin. Okay. So that means you give me an epsilon, and it could be any epsilon. Okay. And then now I'm interested in keeping the solutions within that disk for all future times. Okay, I don't want the solutions to move epsilon farther, larger, to distances that are larger than epsilon. Okay, and then that, given the epsilon, then I search for a delta. Okay, I pick a delta and check. Suppose that in principle I can check all possible initial solutions within that delta. I pick a delta and check whether all solutions starting from all initial conditions within that delta remain in epsilon. Suppose that it's not true. Then I choose a little bit smaller delta and check once again. And suppose that a few of the solutions again move outside epsilon, but after a few trials, suppose that I have been able to figure out some delta, okay, some distance to the origin, and no matter where you start within that little ball, you always remain in this large epsilon ball. Okay? So this is our initial condition, x0. Okay, and this is the direction of time. And then I'm safe. Okay? And then you give me another epsilon, perhaps a smaller epsilon, and then I again try to figure out whether I can find a delta that's small enough so that if I start in delta, I always remain in the epsilon that you gave me. And if that's the case, no matter what epsilon you give me, if I can always find a corresponding delta such that starting in delta I always remain in this large ball, then this equilibrium point, the origin, is stable. Okay. So that's what this definition is telling us. And unstable. Okay. So that's stable, and unstable is you give me some epsilon, and no matter how small I choose delta, but delta should be positive, no matter how much I squeeze further and further this little ball inside epsilon, there always exists some initial condition, okay, within that little ball. And what happens is that eventually it leaves this epsilon ball. Okay. So if I cannot find, no matter how further I squeeze this delta, if always a solution escapes from this epsilon, if there exists such an epsilon, then the equilibrium point or the origin is unstable. And then a certain stable is such that the solution converges to the origin. Okay. And then we have stability, okay, because that's one of the conditions to be satisfied for acidic stable behavior. This is the origin. And on top of stability, we also require attractivity. Okay. So I start here, and at some point I may leave that ball. Okay. Let's start here. Okay. Suppose that I start from here, x0. Okay, and then I may leave the delta ball, but I may never leave the epsilon because the delta is chosen once you have given me the epsilon, and I choose delta small enough so that the solutions are guaranteed to be in epsilon. Okay, so that's stability behavior. But for acidic stability, what happens is eventually the solution or all solutions converge to the origin. If that is the case, then we say that the equilibrium point, the origin, is asymptotically stable. Okay. Now it's very tempting to think that if we have attractivity for the origin, for the equilibrium point, that is, if all solutions starting nearby the origin, they eventually converge to the origin, then it's not difficult to convince oneself that that equilibrium point must be stable. Okay. So even though that seems to be an intuitive deduction, it turns out that it's not true in general, meaning that attractivity does not automatically imply stability. And it's not straightforward, it's not easy to come up with a simple example, but people have come up with a little bit sophisticated examples, and let me now share that example with you. And those of you who are interested can go to computers and simulate it and see for yourself. So here is the question. can an attractive equilibrium be unstable? Okay. The answer is, perhaps it's counterintuitive for some of you. The answer is yes. Answer is yes. Here is an example, and it's not obvious, to me at least, why this example produces attractive but unstable behavior. Here's an example. x1 dot equals x1 square, x2 minus x1 plus x2 raised to the power 5 divided by r squared 1 plus r to the 4. So that's x1 dot, and x2 dot is x2 square, x2 minus 2x1 r square 1 plus r to the 4. They have the same denominator, where r square is x1 square plus x2 square. It's a shorthand notation. Okay. So this is due to, it's a classic example. Okay, it's very famous. It's Vinograd. Okay, that's the author, and it dates back to 1957. Okay. And for this system, the origin turns out to be unstable, yet it's attractive. Every solution converges to it. And for those of you who are interested, you can go and simulate it. And in simulations, you should observe something like this. There may be, okay, so suppose that this is the face plane, and origin is an equilibrium point for the system. And among the solutions, there is this type of a trajectory. Okay, well, there are two trajectories here, and here what happens in that direction, and then in this direction. Okay, so, and then all the other points, they also eventually converge to the origin, but by just focusing on that particular solution here, for instance, it's easy to see that here we have, no matter how tiny we choose, suppose that you give me this epsilon. Okay? Now, no matter how tiny you choose your delta, you can always find some initial condition that lies on that trajectory, okay, somewhere here, and you can get arbitrarily close to the origin. But no matter how further you squeeze this delta, this thing, starting from that initial condition, the trajectory will eventually leave epsilon, and it will go back inside epsilon ball. But according to our definition of stability, the origin therefore is not stable, because for this epsilon, you can never find a delta that's small enough so that starting within the delta ball, you remain in epsilon ball for all future times. Okay, so that's one thing to keep in mind, which is attractivity does not necessarily imply stability. Okay, now let's visit our favorite example, pendulum, and verify what we already know once again by using the now rigorous, precise definition of stability. Okay. Example, pendulum suppose this is the vertical line. This is theta. This is the direction of gravity mg. And let the length of the rod be L. And by choosing the state x1 equals theta, x2 equals angular velocity, theta, we have obtained the following state equation, or system equation: x1 dot equals x2, and x2 dot equals minus g over L, g being the gravitational constant, sine x1 minus k over n. Next to k here indicates the friction coefficient. And we know that this system possesses two equilibria. X equals 0, 0 is a downright equilibrium. We know without any mathematics from our experience from the real world that that equilibrium point is stable. And the other equilibrium point, upright equilibrium point, pi 0, is unstable. Okay, because no matter how close you start to the equilibrium point, unless you exactly start at the equilibrium point, you always move away from it. Okay? Therefore, you can never find this delta for some epsilon, and hence the upright equilibrium point is unstable. Okay, now let's establish by our definition that this downright equilibrium is indeed stable according to our definition. Let us establish the stability of x equals 0, okay, the downright point. And for simplicity, let's ignore friction. Take k equals 0. Okay, with friction, it turns out that, and it's what we expect. The downright equilibrium point is asymptotically stable. Okay, it's not only stable but asymptotically stable. But without friction, if you ignore the friction, then it's not asymptotically stable. It oscillates forever. Okay, but it remains bound. Okay, so with that simplification, letting the friction to be 0, what we have is x1 that equals x2, and x2 that equals minus g over L sine x1. And let's try to, we did this a couple of times already, and it's important because we're going to now generalize this very powerful idea. Let's try to look at or understand the solutions or the behavior of the solutions through the total energy of the system. Okay. So what's the total energy of the system? Okay. Total energy of the system is the sum of kinetic energy of the mass plus the potential energy of the mass. Kinetic energy plus potential energy. Kinetic energy is a function of the velocity of the the mass, okay, 1/2 mv squared, and potential energy is related to how far vertically we are from the equilibrium position, okay? That's the downward equilibrium position. So this is mg times hh, the distance from the equilibrium position. So let's compute, or let's express total energy in terms of our state variables x1 and x2. So this is the vertical line, this is the pivot, this is where we are, mass, and this is theta. And we're talking about the tangential or the translational velocity, v, which is always perpendicular to this rho L. And then suppose this distance is L, okay. Therefore, when the angle is theta, how far this mass is from the vertical reference is what we're calling h. Okay, so this distance is h. Okay. mgh is potential energy, and 1/2 mv squared is the kinetic energy. Now, the translational velocity is radius times the angular velocity, theta dot. So V is theta dot times L. And theta dot was x2, so we have L x2 for V. And as for h, this distance is, so this is L. Okay. This is L, therefore h is L minus this distance, and this distance is L cosine theta. Okay, h is L minus L cosine theta, and that's L1 minus cosine x1. That x1 was theta. Therefore, E, in terms of the state, total energy, in terms of the state, is 1/2 mv squared, which is L squared x2 squared, plus mgh, which is mgl1 minus cosine x1. Okay. Now, as we did a couple of times before, let's figure out the time derivative of total energy along the solutions of the system. Since we're neglecting friction, there's no way that the energy can escape from the system, therefore we already expect a reasonable outcome, which is that E dot equals, or the energy is constant. So let's verify that also using that expression for energy and here the description of the system. So let's now check evolution of energy along the solutions of the system. Okay. In other words, we're interested in what happens, what happens to energy as t moves from the ancient time, which we take v0, toward future times, toward infinity. And for that, it's always a good first step to try to compute its time derivative. Let us compute d over dt, time derivative of the solutions pass through the energy function. D over dt E of x of t is d over dt E of, no, that x of t is the state vector x1 and x2 together. Therefore E is a function of x1 and x2, which is what it actually is. Okay, function of x1 and x2. All the rest are constants. So E of x1 of t and x2 of t, that's what we're trying to figure out. And if you have such a function to compute time derivative, what you do is you take partial with respect to the first argument, and then you take the time derivative of the first argument, plus you take partial derivative with respect to the second argument, and then you multiply that with the time derivative of the second argument, and so on. You go as many times as the number of variables that you have. In this case, we have 2 variables because the order of the system is 2. So this means that we have to compute partial E1, partial x1 times dx1 dt plus partial E, partial x2 times dx2 times dt. Okay. And that can be written as the inner product of 2 vectors, partial E, partial x2, okay, times x1 dot, x2 dot. Okay. Now, this thing is what we're calling x dot, the time derivative of the state, and that equals the right hand side, which we denote by f. And this thing here is partial E with respect to the vector x, and this, according to our definition, is transpose of the gradient. Note that the gradient and this notation, they're the same, almost the same. The difference being that this is a row vector, and in some other context, in some other text, it can be the other way around. So this is not a really universal notation, but within this course we'll stick to the following notation. This is a row vector, and this is a column vector. Okay, and here we, since we have a row vector here, therefore we have to take the transpose of this gradient, which is a column vector. Okay, so therefore this is the gradient of the energy taken inner product by the right hand side of our system of x, and this is no other than time derivative of the energy along the solutions of the system whose right hand side is described by f. Okay, so it's a very nice compact notation that we will be using on and on throughout this course. Okay. Now this is true in general. The notation that we have just obtained is true in general. Given a function which maps points in Rn to the real line, or like the energy function that we're using. Energy is always scalar, and a system, an autonomous system, x that equals f of x, where x resides in Rn. F is a mapping from Rn to Rn. We have d over dt v of x of t. So what you do is you combine two things and obtain a scalar function of time. How you combine two things? You combine v. Okay, the argument of v is Rn. So what you do is within that argument, you take the solution of the system starting from some initial condition, which is x of t, and you plug in x of t as the argument of v, okay? And then you can consider that construction as a mapping from R to R, okay? Where a mapping from t to the real line, okay? Therefore, it's a scalar function of time. Therefore, we can talk about its derivative. Okay? And its derivative is computed as what we have discovered here. That equals the gradient of v of x, okay, with respect to x, and you take that inner product y f of x. And this is, from now on, what we'll be meaning when we say v dot, okay, for v being such a function. Okay, now let's return to our example. Okay, E dot equals the inner product of the gradient of the energy function. The partial of energy function with respect to x1 gives us ngl sine x1. Okay, and the gradient with respect to x2 gives us nl square x2. This vector we're taking the product with right hand side x1 that equals x2 and x2 that equals minus g over l sine x1. Okay, this times that plus this times that, and that is 0. And that equals mgl sine x1 times x2 minus ml square x2 times g over l sine x1. Okay, this l will cancel one of the l's over there, and those two sides become equal in magnitude but opposite in sign. Therefore, we get what we expected. Since there is no friction, energy will remain constant for all future times. And now let's interpret what E dot equals 0 means. That's what we're going to do. And from that interpretation, we'll follow the stability of the downright equilibrium position. Okay. Meaning of E dot equals 0. Is the trajectories will always move along the curves that are defined by E of x energy equals some constant, and that constant is the initial energy, the energy at t equals 0. Curves where by a constant we mean initial energy E of x of 0, the energy at t equals 0. Okay. Now let's try to figure out the shape of those curves, and then by looking at those shapes we can introduce circles or balls to the phase plane, and then we can deduce stability, because the definition of stability is given in terms of balls. Okay, something less than equal to the norm of, or the Euclidean distance of the state being less than some positive number. So shape of E of x equals some constant. Okay. Now E of x equals 1/2 ml square x2 squared plus mgl 1 minus cosine x1. Okay. Now to have an idea of what the shape will look like, let's consider the case where we are close enough to the origin. Okay. And for that, we write cosine x1 as its expansion plus x1 to the 4 over 4 factorial minus x1 to the 6 over 6 factorial plus and so on. Okay, so that's cosine x1. So that means cosine x1, if you somehow are interested in the small x1 case, cosine x1, you can ignore the higher order terms and you can approximate nicely cosine with this function, 1 minus x1 squared over 2. So cosine x1 is approximately equals 1 minus x1 squared over 2 for small x1. Okay. So x1 was the angle, so that means if the angle is not that far from the equilibrium position, then you can approximate this cosine x1 with 1 minus x1 squared over 2. And if you do that, it's easy. This becomes easier to interpret from the shape point of view. Therefore, for small x, that is, for a state not far from the equilibrium position, we can write E of x approximately equals 1/2 ml squared x2 squared plus 1/2 mgl x1 squared. Okay? Because if you plug in cosine x1 equals 1 minus x1 squared, then this 1 minus cosine x1 becomes x1 squared over 2. And then you have 1/2 mgl x1 squared. So these are all positive constants. That what we have is, as E of x, an approximation for small enough x. It's some constant times x1 squared plus some other constant times x2 squared. If those two constants are the same, we have a circle. If they're different, then we have an ellipsis. Okay. So therefore, the solutions must stay on those ellipses for all future times. Okay. And what ellipse that our particular solution will stay on, and that's determined by the initial condition. Okay. So here, one ellipse. Here is another ellipse. So this is x1, x2 plane. Okay. So here, this is E of x equals some constant. And here, this curve is E of x equals some other constant. And as you move farther and farther, as your ellipse becomes bigger and bigger, means that this constant is becoming larger and larger. So in this case, it must be that C2 is larger than C1. Okay? So this is the phase portrait, at least for small initial condition x0, because our ellipsis approximation is valid for small state. Okay. And now, by looking at those shapes, we will be able to apply our definition of stability and deduce or establish rigorously what we have known all along. That is, the downright equilibrium position is stable. Okay. Now, recall the definition of stability. Okay, that is, you give me any epsilon, if I can find some delta, okay, small enough so that starting in delta, I always remain in epsilon, then that equilibrium point is stable. So, suppose you give me some delta. This is x1, x2 plane. Okay. Excuse me. Suppose you give me some epsilon. And then what I want is, I want the norm of Euclidean distance of the state or the solution to be less than equal to epsilon for all future times. First, let me draw that epsilon disk. Okay, this is our epsilon disk. Now, what I need is, I need a delta, so that the disk with radius delta will be my possible, my set of possible initial conditions. And whenever I start in that disk, I never leave this larger disk. And how to choose delta? Well, here we have ellipses, and the solution starting on an ellipse will always remain on the ellipse. Okay, so what I will do is, I'll choose an ellipse that touches my epsilon circle. Okay. Now, this is a solution, a periodic solution. And if it starts, if the system starts on one of the points on that ellipse, it will always remain on that ellipse. And now, next question is how to choose delta. Now, how you choose delta is, we put the ellipse inside epsilon, and now we put delta inside the ellipse. Okay. Okay, and this is my delta 1. And now, for this epsilon, I claim that for all initial conditions starting in this delta disk, all the solutions will remain within epsilon. Why is that? Suppose that for some initial condition, suppose that it's not true. For some initial condition delta, I leave epsilon 1. Okay, so let's see that that causes a contradiction. I start in delta and I leave epsilon. But before, I have to leave this ellipse. Okay, I have to cross ellipse before crossing epsilon, because ellipse is within epsilon 1. But when I touch my solution, which supposedly will cross the epsilon, will go outside epsilon, then my solution touches or intersects the ellipse at some point. It cannot go outside the ellipse, because we know that once you're on the ellipse, you always remain on the ellipse. So once you're in the ellipse, you always remain epsilon. Therefore, no matter where you start within this delta ball, you will never leave epsilon. And this is true for any epsilon you give me. For any epsilon you give me, I can apply the same argument, and I can always find an appropriate delta. So that starting in delta, I never leave epsilon. Therefore, according to our definition of stability, the downright position, which is our origin, according to our notation, is stable. Okay. So x0 less than or equal to delta implies x of t less than or equal to epsilon for all future time. Therefore, the origin must be stable. Is now let's make quick observations, which we will generalize in the next lecture. Okay. Observe that without explicitly computing the solution x of t, we have determined of the equilibrium point, the origin, 0 through an energy function, okay, E of x. Now the energy is in quotes because later on we will generalize that function to, well, to domains where it's not necessarily representing the energy but something else. And E of x locally at least satisfies Ex is positive for all states outside equilibrium, okay, and at equilibrium it's 0, and this is what we're going to call positive definiteness. Okay, such functions we will call positive definite. And finally, E dot x satisfies E dot x. In our case, it was equal to 0 because we took the friction out of the picture, but if we had friction, we would have less than equal to 0. So therefore, we can write the general case that E dot is less than or equal to 0. And this is negative semi-definiteness. Okay. And these observations that we collect from this simple example had been generalized by Lyapunov in the beginning of the 20th century to a very powerful tool to check stability of equilibrium. Okay. And in our next lecture, we'll be talking about that. We will try to establish stability through positive definite functions, okay, whose derivatives along the solutions of the system are negative semi-definite.